Ever stop to think about how a metal wire and a simple glass of salt water can both do the exact same thing, light up a bulb? It's kind of weird, right? They both conduct electricity, sure, but what's going on inside them is a completely different story. So in this explainer, we're going to unravel that mystery and get right to the heart of the difference between electrical conductors and electrolytes. I mean, on the surface, it looks identical. You complete a circuit with a copper wire, the bulb lights up. You do it with salt water, and bam, the bulb lights up again. It's so easy to just lump them together and say they're both conductors. But is the same thing really happening inside? That's the big question we're going to crack today. Okay, to solve this puzzle, we've got to zoom way in. I'm talking microscopic level. We need to see what's actually moving around in there, carrying that electric charge from one place to another. So let's meet our tiny charge carriers. At its most basic level, an electric current is just that, a flow of charged particles. And trust me, that word, particles, is the most important word on this slide. Because as you're about to see, the type of particle that's doing all the moving, well, that changes everything. So here they are, the two main players in our story. On one side, you've got mobile electrons, these super tiny, negatively charged particles that are free to just zip around. And on the other side, you have mobile ions. Now, these are whole atoms that have either gained or lost an electron, which gives them a charge. These are our two completely different ways of carrying a current. All right, let's start with the one we all know and love. Let's take a look at how electricity flows through a regular old piece of metal, like that copper wire we were talking about. This is the electron's time to shine. If you look at the periodic table, you'll see most of the elements are metals, and they all have this really cool atomic structure. Their outermost electrons aren't really tied to any one specific atom. Instead, they form this kind of sea of electrons that can just flow freely through the entire structure. Think of it like a huge crowd of people wandering around a giant hall. They can go wherever they want. So, when you connect a battery to a piece of metal, you're essentially giving all those free-moving electrons a push. They all start flowing in the same direction, and that flow is the electric current. It's that simple. For metals, the charge carriers are electrons. Period. And here is a super important point. While all those electrons are zipping around, the metal atoms themselves are just staying put. A copper wire is still a copper wire after electricity has passed through it. Nothing about it has chemically changed. It hasn't broken down or turned into something new. Okay, now let's completely switch gears and look at our other case, electrolytes. The way they work is fundamentally different. This is where the ions, not the electrons, take center stage. First off, where do these ions even come from? Well, let's take table salt, or sodium chloride. What happens is the sodium atom actually gives one of its electrons to the chlorine atom. This little transfer leaves the sodium with a positive charge and the chlorine with a negative charge. And just like that, you've got ions. So an electrolyte is basically any compound that, when you melt it down or dissolve it in something like water, breaks apart into these mobile ions. And mobile is the absolute magic word here. Because if you have a solid crystal of salt, those ions are locked in place. They can't move, so solid salt can't conduct electricity at all. But the moment you free up those ions, things get interesting. You stick a couple of electrodes into the liquid, apply a voltage, and the ions start moving. All the positive ions head towards the negative electrode, and all the negative ions head towards the positive one. It's this physical movement of entire ions that makes up the electric current. So, to be crystal clear, in electrolytes, the charge is carried by mobile ions. It's not a sea of tiny electrons flowing around. It's the big, chunky ions themselves physically moving through the liquid. And this leads to a massive difference in the outcome. When those ions finally reach the electrodes, a chemical reaction happens. They actually turn back into neutral elements. This means the electrolyte itself gets broken down. It's decomposed. It's a permanent chemical change. The stuff you started with isn't what you end up with. Okay, we've seen both sides of the coin. Now let's put them side by side, a little head-to-head comparison to make these differences impossible to forget. This table really sums it all up, doesn't it? Let's break it down. First, the charge carrier. In a conductor like copper, it's mobile electrons. In an electrolyte, mobile ions. Totally different things. Second, the state. Conductors are usually solid, maybe liquid, but electrolytes have to be molten or dissolved. And finally, the big one, chemical change. For a conductor, absolutely not. For an electrolyte, yes, it always gets decomposed. So here's the one sentence I want you to remember from all of this. Ready? Not all conductors are electrolytes, but all electrolytes are conductors. Think of it this way. An electrolyte is just a special type of conductor, one that happens to use mobile ions to get the job done. All right, enough of me talking. You've seen the theory, now let's see if you've got it. Time for a quick challenge to put your knowledge to the test. First one up, an iron nail. Okay, we know it's a metal, so what does that tell you about what's carrying the charge inside? And think about it, would running electricity through it cause the nail to just fall apart? So what is it? Conductor, electrolyte, or maybe neither? Okay, next up, a block of solid table salt. We know for a fact it's made of ions, a whole bunch of them. But are those ions free to move? What was that magic word we needed for conduction in an electrolyte? What do you think? All right, for our last challenge, let's take that same salt and melt it. Now it's a hot liquid. So what about those ions now? Are they free to roam around? How does changing the state completely change the game here? Conductor, electrolyte, or neither? And that really brings us to the most important takeaway of all. The real question you should be asking isn't just if something conducts electricity. The real question is how it conducts. The next time you see something that conducts a current, just ask yourself, what's moving inside? Is it a sea of electrons, or is it a bunch of mobile ions? You answer that one question, and you'll have it right every single time.